Okay, welcome back. We are working on 1-3. We're going to introduce the concept of trig functions. We're going to start with them focusing on trig functions as related to an angle in standard position, an angle of rotation on an xy coordinate plane that is in standard position. So to get a basic grasp of what we're looking at, we're going to start with any angle theta in standard position with point P on the terminal side at some coordinates xy. So remember that we have our initial side of our angle in standard position is the positive x-axis, and let's just rotate our angle theta somewhere in quadrant 2. So here is my very unstraight terminal side, but here's my rotation, here's my angle theta right here that I'm looking at. Now I could have stopped in quadrant 1, I could have rotated all the way around. It really doesn't matter. I just picked a spot. And I have point P at some xy coordinates on the terminal side of my angle. Now, to figure out how to measure this angle, I am going to drop a perpendicular. Let me change colors here. I'm going to draw a perpendicular line perpendicular to the x-axis from point P. So I'm going to drop a perpendicular line down to the x-axis. Remember, we're always going back to the x-axis. So wherever, if P had ended down here, that perpendicular would have gone up. If I'd rotated all the way around to quadrant 4, my perpendicular would have gone to the closest x-axis. When I drop that line that's perpendicular to the x-axis, I've created a right triangle. P has coordinates x, y. In this case, x is negative, y is positive. And r is that length of the hypotenuse, the side opposite the right angle, and it's this length right here of this side. So r is the distance from P to the origin, which is the vertex of my angle when it's in standard position. Now, r is any real number. It can be any distance. It can be any length. My point P could be as far out as I wanted it to be or as close in as I wanted it to be on this terminal side of my angle. R stands, think of R as for radius. If I continued to rotate this angle, that would be the radius of the circle that would form. So I have created a right triangle, OPQ, where this is my origin, and we're going to say this is point Q here. Now, how do I figure out how long r is? Well, r is related to this value coordinates xy, the distance out from the origin on the x-axis and up from the origin on the y-axis, horizontal and vertical shift. Also, hopefully you remember that with right triangles you have the Pythagorean Theorem, so that we know that a squared plus b squared equals c squared, where c is my hypotenuse. Well, if I want to solve for the length of that hypotenuse, I would take the square root of both sides. Since we're talking about measurements of distances on that triangle, everything's going to be positive. So when I take the square root, I don't have to worry about plus or minus. So my Pythagorean theorem tells me that a squared plus b squared equals c squared, where c is the length of the hypotenuse, so I can solve for c. Putting this in terms of our right triangle, we have that r, the length of my hypotenuse, is the square root of the sum of the squares of the two legs. This is my distance formula. Gives me the length of side r. Okay, now this next bit on this first page is not something that you have to memorize at all, but as we introduce our 6 trig functions, cosine, sine, tangent, secant, cosecant, and cotangent, as we introduce those 6 trig functions, I know that a lot of people really like to have something to put their finger on. They like to have something that they know this is what we're talking about. Well, each of these is just a picture of our first quadrant. So think about if you were to extend these lines. This is my xy axis, x-axis, y-axis. So this is quadrant 1. And I have rotated an angle theta and stopped in quadrant 1 this time. It's just easier to show it all in quadrant 1. And then here's my circle, the part of the circle that falls through quadrant 1. And in that I have a right triangle here. And then I have a larger right triangle here, right? Okay, well each of my 6 trig functions can be expressed as lengths of line segments that are related to that angle theta. Cosine is this segment right here, the distance out on the x-axis. Sine is this segment right here, the distance up. Tangent, if I were to extend this radius line and then done a perpendicular up from the point where that radius touches the x-axis, it goes through here. This is my segment for tangent. You see that's on that larger right triangle. The smaller right triangle and the similar larger right triangle. That is that distance here. It's tangent to my circle. Secant segment is that extended distance that makes the hypotenuse on the larger of the 2 similar right triangles. Cosecant would be if I drew a line that's perpendicular to the y-axis out this way and extended it all the way here. That's the segment that is represented by cosecant. And then finally, this is my cotangent line right there. Okay, so again, this is not a visual that you're going to have to memorize. I think that I've got it stuck in the notes later on as well, but it's just a good physical reminder of these are the things that we're looking at. So for those of you who really that's helpful for, you have a visual, okay, this is what I'm talking about when I'm talking about cosine. This is what I'm talking about when I'm talking about cosecant. Okay, let's look at that next page of notes. Here are my definitions of my 6 trig functions in reference to an angle in standard position. So we're going to talk about trig functions in a couple of different ways this semester. We're going to talk about them right now. We're talking about them on the unit circle and standard position. We're also later on going to do some right triangle trig that is just based on a triangle somewhere out in space, not positioned on an xy coordinate plane. So we're defining our trig functions in relationship to an angle in standard position. We've talked about this distance formula where r is equal to the square root of the sum of the 2 squares of the sides x and y. We've got sine, cosine, and tangent as our 3 basic trig functions. Those are the buttons that are going to show up on your calculator. Their reciprocals are cosecant, secant, and cotangent. And these do not have buttons on your calculator. Now, I don't have my calculator again today, but I will grab that before our next section so we can look at the calculator some. But if you look at your 3 basic trig functions and their reciprocals, reciprocal, remember, if I take the reciprocal of a fraction, so if my fraction is 2/3, the reciprocal would be 3/2. I flip it. Same is true for these reciprocal functions. Sine theta is defined as y over r. Cosecant theta is defined as r over y, as long as y is not 0. R is never going to be 0, so we don't have to worry about r in the denominator. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. I remember these two by saying S pairs with C. Sine pairs with cosecant. Cosine pairs with secant. So these are the 3 basic trig functions. These are their 3 reciprocal functions. Now, on the unit circle, on what we call the unit circle, which we haven't looked at quite yet, we will look at soon, r is 1. But this is going to work with any value. Sine theta, if r is 1, sine theta is just y. That's that y, length of that y segment. Cosine theta is just x, the length of that x segment. This is going to work with any value because the ratio, how y compares to r, is always going to simplify to the same value. Okay, so we have our basic three functions and their reciprocal functions going across this way. These pair up another way. They pair up as cofunctions. Cofunctions, if I look at them like this, sine and cosine are cofunctions, secant and cosecant are cofunctions, tangent and cotangent are cofunctions. So they pair up that way as cofunctions. Cofunction, I have a cofunction theorem that we're going to focus on next section in 2.1. The cofunction theorem says that the value of a trig function of an angle is equal to the value of the cofunction of its complement. So for example, if I'm thinking about tangent and cotangent, the tangent function value of 30 degrees is going to be equal to the cotangent value of the complement of 30 degrees. Well, remember, complement, an angle and its complement add to 90, so the complement of 30 degrees is 60 degrees. I could say that sine and cosine are cofunctions. I could say that the sine of a 20-degree angle is going to be equal to the cosine, cofunctions, and then I need the complement of a 70-degree angle. So those are examples of my cofunction theory. Alright, so we have angles and their reciprocals, or trig functions and their reciprocals, that pair up like this. And then we have cofunctions. Now tangent and cotangent both happen to just happen to be both reciprocals and cofunctions. Alright, so let's do a couple of examples of finding these function values. The terminal side of angle theta in standard position passes through the point 12,5, and we need to find the values of the 6 functions. Now we're not going to rely on our calculator. We're going to put the values together, keep them exact. We're not going to estimate. So we need to sketch our angle theta. Angle theta goes through the point 12,5. Well, 12,5 is going to be in quadrant 1. Let's say this is the point 12,5. We're in quadrant 1, so here's my angle theta. I've moved over 12, and I misdrew my angle a little bit. It should have been longer and not as far up. We're going to go with it. My x-coordinate is 12, my y-coordinate is 5, so I moved over 12, up 5. I am missing the value for r, so I have to use my distance formula to find r. Well, r is going to be the square root of the sum of the squares of the legs of the right triangle. So I've got 12 squared plus 5 squared. So r is the square root. 144 plus 25 is 169, and the square root of 169 is 13. So r is 13. So I have a value of x as 12, y as 5, and r is 13. Those are the 3 values I need to know to build my 6 trig functions. Now we see how the 6 trig functions get built in relation to x, y, and r. So I have my 3 basic trig functions: sine theta, cosine theta, and tangent theta. Sine is y over r, so 5/13. Keep it exact. Cosine is x over r, so 12/13. And tangent is y over x, so 5/12. Now once I've done those three basic trig functions, I just flip them over to get their reciprocals. The reciprocal of sine is cosecant, the reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. So the reciprocal of 5/13 is 13/5, 12/13 becomes 13/12, and 5/12 becomes 12/5. And those are my 6 trig functions. We're going to keep them exact unless our instructions tell us otherwise. Okay, we're going to do one more like this. This time we have, the point is 8, -6. That's not in quadrant 1. So let's see what happens to our perpendicular that we drop when we're not in quadrant 1. Well, 8 is a positive x value, negative y value, so 8, -6 is going to be down here somewhere. So here is my value, my angle theta, but my angle theta that we're looking at is rotated this way. This is angle theta, this reflex angle here. Even though this is the angle I'm interested in, angle theta, remember your perpendicular always goes to the closest x-axis. So my perpendicular is going to go here. There's my right triangle. X is a positive 8, y is a -6, and we need to figure out r. So I'm going to use my distance formula again, square root of the sum of the squares. Now when I square a negative, it becomes positive. 8 squared is 64, -6 squared is 36, so r is the square root of 100, or r is 10. Alright, I've got r is 10, x is 8, y is -6. Making that little chart always helps me to make sure I don't get confused when I start setting up my 6 trig functions. Basic functions, sine theta, cosine theta, tangent theta. I'm going to start here. Sine is y over r, so I've got a -6 tenths. Oh, and that's going to simplify, isn't it? So that becomes a -3/5. There's sine theta. Cosine theta is going to be 8 over 10, which is going to simplify as well. And tangent theta, y over x, is -6/8, which is -3/4. So notice, because I'm in quadrant 4, anything that has a y involved is negative. Sine is negative, tangent's negative, cosecant is going to be negative, and cotangent is going to be negative. So there's my reciprocal trig functions, secant theta, and cotangent theta. So sine to cosecant, this becomes, sine to cosecant, this becomes a -5/3. Cosine to secant becomes a +5/4, and tangent to cotangent becomes a -4/3. All right, excellent. Okay. Just a couple more examples. Finding function values of an angle when we are given an equation for the line. So this one looks a little different starting out. We're not given coordinates for a point, we're given the equation for a line, and we're told to restrict ourselves to where x is less than or equal to 0, so x is going to be negative. That's the part of the line that we're interested in, where x is negative. Okay, so let's take our equation for our line and let's pick a negative value for x and plug it in and see what happens. Let's say, and x can be negative anything. Let's say that x is going to be a -2. So if I have my equation for my line and I plug in a -2, and -2 is not special. I could have picked -5 or -12 or -1. It really doesn't matter. I just know that I needed a value for x that was negative. So I need to find a y coordinate so I know a point that this line is going to go through. That gives me -6 minus 2y equals 0. So -2y would be +6 when I move that over and finish solving for y. I get that where x is -2, y is -3. So where x is -2, y is -3. That's the coordinates of a point that is on this line. Now I'm only interested in the part of the line where x is less than or equal to 0. So I'm only going to draw this part of the line. So my line is going to stop at the origin. My line includes all the negative x values, stops at the origin. So there's my angle theta. Right there's my angle theta. And I draw that perpendicular to the closest x-axis. I've got my right triangle formed. X is -2, y is -3, and we need to figure out r. Now once we figure out what point, at least one point, we only need one point because we know our line is going to go through the origin. A point that falls on that line, we have our three values for our triangle, and we can come up with our 6 function values. So for this particular equation, we used x as -2. We found that where x is -2, y is -3, and r is going to be -2 squared plus -3 squared. 4 plus 9 is 13. So r is square root 13. Now we're going to have to deal with that radical. We don't leave radicals in the denominator of fractions, so we're going to have to rationalize our denominators. Okay, sine theta, cosine theta, tangent theta are 3 basic trig functions. Sine is y over r, so -3 over square root 13. Cosine is x over r, so -2 over square root 13. And tangent is y over x. Negative over negative is a positive, so that's just a positive 3/2. Okay, now I need to rationalize these denominators. I don't leave that radical in my denominator. To rationalize a denominator, I multiply square root times square root, gives me that square root squared. So think about that. Square root 13 times square root 13 is square root 13 squared. And that square and that square root cancel out and just leave me with 13. So my denominator is 13. My numerator becomes -3 square root 13. That's the sine function value. Now, the square root did not disappear. I just rationalized it. It moved it up into the numerator because that's best practice mathematically. It's standard that we don't leave a radical in the denominator. I will do the same thing here and end up with -2 square root 13 over 13 for cosine. And then tangent is just 3/2. Now, when I come back and I do my reciprocal function values, cosecant theta, secant theta, and cotangent theta. Cotangent theta is easy, it's 2/3. But when I do cosecant and secant, the reciprocals of these two, I'm going to look back at my starting place before I rationalized, because flipping this one is a lot easier than having to unrationalize. When I take the reciprocal of what I started with for sine, I have a negative square root 13 over 3. When I take the reciprocal of what I started with for cosine, I have a negative square root 13 over 2. So there's my 6 trig function values. One other thing I wanted to point out, if I took my equation for my line, 3x minus 2y equals 0, and I solved for y to put it in slope-intercept form, I get that y is equal to 3/2 x. I see that my tangent value is the slope of that line. And that is always going to be true. Tangent theta is the slope of the line. That's a neat way to check yourself. Okay. Finding function values of quadrantal angles. What is a quadrantal angle? Well, a quadrantal angle is an angle that lies on the x or y axis. It lies on that quadrant of my circle. Now, for these two, it didn't give me any specific values, so I can use my unit circle. I can say, all right, I have my unit circle here where r is 1. So that's 1, this is -1, -1. 1, 0, 0, 1, -1, 0, and 0, -1 is my coordinates there. An angle of 90 degrees is right here. That's my first quadrantal angle, 90 degrees. If I am looking at the 6 trig function values for an angle of 90 degrees, I'm thinking about if r is 1, and r is 1 here, then sine is y over r, Well, sine, if r is 1, 1 over 1 is just 1. So sine theta is just 1. Cosine theta is x over r. 0 over 1 is just 0. And tangent theta is y over x. Well, if x is 0, 1 over 0, if x is 0, 0 in the denominator, that's undefined. When I flip these, I've got cosecant theta, secant theta, and cotangent theta. 1 over 1 is still just 1. 1 over 0, though, is undefined. And cotangent becomes 0 over 1, which is just 0. Let's think about if I did 360 degrees. That's another quadrantal angle right here. So that x is 1, y is 0, and let's just make r 1. So x is 1, y is 0, r is 1. So here, sine y over r, sine is going to be 0 here. Cosine is going to be 1. Tangent is going to be 0 because it's 0 over 1, y over x. And when I flip these to get the reciprocal function values, 0 goes to the denominator, that's undefined. 1, the reciprocal of 1 is just 1. The reciprocal of 0 is undefined. 0 goes into my denominator, that's undefined. Alright, for C and D, I'm given a point that I need to put on my xy coordinate plane. For C, my point is at 0, negative 5. So that's right here. That would be a 270 degree angle, 0, negative 5. So if this is negative 5, I have x is 0, y is negative 5, and r is going to also be negative 5. Right? Is r negative? Let's stop and look at that. R is square root of the sum of the squares. 0 squared plus, look at that. When I square that negative, it becomes positive. Square root of 25 is a positive 5. So r is a positive 5. There we go. All right. Sine, cosine theta, tangent theta. Don't drop the theta. Make sure you're writing your argument down. Sine is y over r. Negative 5 over 5 is negative 1. Cosine is x over r. 0 over anything is 0. Tangent is y over x. 0 in my denominator is undefined. Then I set up the reciprocal values. Reciprocal of negative 1 is still going to be negative 1. Reciprocal of 0, that puts 0 in my denominator, and that is undefined. If something starts as undefined, that means 0 is in the denominator, so when I flip it, 0 is in the numerator. Alright, one more of these. I encourage you to stop and do this on your own, pause the video, do it on your own, and then come back and see if you get the same thing I get. My point I'm given is a negative 3, 0. So there's my angle theta. This gives me x is negative 3, y is 0. R is going to be a positive 3. Remember, if we do r, it's be negative 3 squared plus 0 squared. Square root of 9 is 3. R is a positive 3. R is always going to be a positive value. Sine in this case is 0. Cosine negative 3 over 3 is a negative 1. Tangent, y is in the numerator, tangent is going to be 0. And once I have those three basic function values, I take the reciprocals. Reciprocal of 0 is undefined. Reciprocal of negative 1 is negative 1. And the reciprocal of 0 again is undefined. Okay. Excellent, excellent.